So, in an earlier video we introduced electrolysis. And electrolysis is the process where you're taking some electrical energy in order to cause a reaction that ordinarily doesn't want to occur. And in the previous video we talked about a very famous example of this, which is the electrolysis of sodium chloride. Alright, and that happens when you have this reaction vessel where you have molten sodium chloride, and at the cathode you end up reducing your sodium ions into sodium metal, and at the anode you end up oxidizing your chloride ions to make chlorine gas. Right? And one thing I wanted to point out about this particular example right here is that there's absolutely no water in this vessel. Alright, this is pure melted sodium chloride. Alright, if there were any water around here, it would immediately boil away because of the temperatures that are required to melt sodium chloride. Alright, but a lot of the more famous examples of electrolysis occur in situations where this is an aqueous solution. Alright, so that's what this video is going to be talking about. And we're going to start off with the most famous example of this, which is just the plain old electrolysis of water. Alright, so so in the earlier Tyler DeWitt video, he talked about the oxidation and reduction reactions that occur with water, and he talked about them in regards to their oxidation numbers. But I want to introduce them in a slightly different way, and that's just by counting electrons. Alright, you can recognize the process just by trying to figure out, hey, are electrons needed for this reaction to occur, or do electrons need to be taken away for this reaction to occur? Alright, so just for reference, I've drawn the structures of hydrogen and oxygen molecules right here. Recall that a hydrogen molecule is two hydrogens with a single bond, so there's two electrons there. And this is the structure of oxygen. You can count that there's 2, 4, 6, 8, 10, 12 total valence electrons in that molecule. Alright, so in the reduction of water, alright, this is going to be where the hydrogen atoms in the water get reduced to make a hydrogen molecule. Right? One way to think about it is to first say, well, let's take these electrons in this bond right here, and what if we did this, where these electrons from this bond went onto the oxygen? All right, that would essentially give all of this right here. All right, again, you have two electron pairs here on the oxygen, and when these electrons go into the oxygen, that creates a third electron pair. So these two guys right here, hopefully you recognize these guys as hydroxide molecules, which we normally represent like that. All right, but when these electrons get pulled away, you'd be left with this little piece right here, and that's just a hydrogen, but without these electrons. All right, and what that would be is H+. All right, and we would have two of those. You'd have one from this guy and one from this guy. All right. So what I want to draw your attention to is to compare these two H pluses to what we need to have in order to have a molecule of hydrogen. All right, notice that there's something missing. There are these two electrons here that are needed to form the covalent bond. So in order to get from here to here, we have to add two electrons. All right, that's the piece that's missing. All right, and so that's why this is considered a reduction. This process of going from the water molecules, where this is essentially, these are all the same parts of water right here, in order to get from the water molecules to the hydrogen molecule, we need to add two electrons. All right, so if you took this overall process right here, what you have are the two water molecules, all right, plus the two electrons that are needed for the reduction, all right, and that would make a hydrogen molecule and two hydroxide polyatomic ions. All right, so we're going to shift our focus to the oxidation step. All right, again, we're going to start with two water molecules, and again, we're going to basically represent this as its parts. All right, let's imagine that we could draw a little curly arrow that goes from this bond and from this bond to the oxygen. Right? Same thing down here. So when that happens, here we have 2 electron pairs on the oxygen. If we add 2 more from the electrons in these bonds right here, we would have our oxygens would look like this. All right. So and also we would have the 4 H pluses, which happens, which we would get from these 4 hydrogens once the bonds are broken. All right. So just by comparison, let's look at an oxygen molecule, and it looks like that. And so, actually, we can use this guy right here. Let's count. Okay, we've got 2, 4, 6, 8, 10, 12 total electrons in the oxygen molecule. But between these two right here, we have a total of 16. All right. So in order for these 2 guys to become this guy, it's got to lose 4 of those electrons. There's too many electrons between these 2 oxygen atoms to make this right here. So that's why we're going to draw the 4 electrons right here. These are the 4 electrons that this oxygen had to get rid of in order to make this molecule. All right. So again, we can draw this overall reaction as 2 water molecules, because we had 2 water molecules right here. Make the 4 H pluses. Those would be right here, plus this oxygen molecule, plus the 4 electrons that had to get spit out. All right. So where is this happening in the actual electrolytic cell? All right. So again, this doesn't happen all by itself. It needs to have electricity put into it. We're going to do that with the use of some form of battery. The negative end of the battery is going to push the electrons towards the cathode, and this is where the reduction process is going to occur. All right. So essentially, water molecules are going to be at the surface of this electrode, and they are going to be accepting the electrons. All right, and the electrons are going to allow the hydrogen molecules to get formed, and those H2 bubbles are just going to bubble away. All right. So I want to point out that the electrons in this equation right here are actually supplied by this process right here. If it isn't for the electrons being pumped in by the battery, there would not be electrons to allow this to occur. All right. So on the other side, we've got the anode. All right, and this is the process where you've got water molecules surrounding this electrode, and you're going to have this reaction occur. And the thing that drives this reaction is the fact that electrons are being strongly pulled away. All right, remember, for this to happen, electrons are going to be created, and unless these electrons get pulled away, this reaction is going to stop. All right, and that's what the battery does. It pulls those electrons away, and your oxygen product is going to form bubbles right here, and those are just going to bubble away. All right. So what I want to point out is what is the overall reaction happening in the cell? All right. Well, we could write the oxidation reaction right here, and we could write the reduction reaction below that. And if we wanted to say overall what's happening, well, we could do a little trick that we did before when we were trying to balance redox reactions, which is we wanted to make sure that we had the same number of electrons being transferred. And if you look here, we've got 4 electrons as a product over here, but we've only got 2 as a reactant right here. So what we need to do is we need to multiply the bottom one by 2. All right. So if we multiply the reduction reaction by 2, we end up getting this right here. So now what we want to do is we want to add this reaction right here to this reaction right here. And the reason that we can do that is your 4 electrons right here would cancel with your 4 electrons right here. So adding these 2 water molecules plus these 4 water molecules gives us 6 water molecules. Bring everything else down. All right, again, those electrons right there are not there anymore. And one thing I want to point out is that I'm saying 4 H2Os. All right, well, where did those come from? All right, well, where they came from is the fact that you have 4 H pluses here and 4 OH minuses here. And every time a hydrogen, an H plus, combines with an OH minus, you make water. All right, remember that the self-ionization of water reaction, hopefully that would be familiar. All right, so if you look at this combined reaction, you'll notice that we've got the same product on both sides. So if we got 4 over here and 6 water molecules over here, we can cancel this guy out, and that's going to become a 2 right there. All right, so that reduces down to this overall reaction.